And it doesn't ask us to do this, but maybe we'll just kind of do it together to remind ourselves of some stuff that we did last time. If I wanted to plot 1/2 plus I root 3 over 2, starting at the origin, where do you go for this 1/2? Which direction do we go? We go to the right 1/2. And what about this I root 3 over 2? We go up. How do you go up I? You just go the root 3 over 2. The I is embedded in that vertical axis, right? So we're going 1/2 to the right, which is around there. Root 3 over 2, you can type it on the calculator. It's like 0.866. So that's somewhere near towards the top. And we get the 1 point right here. So that is Z. And I'd really like us to buy that that represents the same thing as e to the I times pi over 3. So first I'm going to stick a number in the front. What's the number in the front of the e? It's 1. Got to have a number in there. And that 1, remember, is the r. It tells you how far you're walking from the origin. Do you buy that perhaps walking from the origin to that point is 1 unit? Could it be? Could be, couldn't it? I mean, like if I wanted to walk 1 unit to the right, I land here. If I go 1 unit up, it's here. 1 to the left is here. 1 there. If I draw all the points that are 1 unit away from the origin, what's that shape? It's a circle. In fact, it's the unit circle, the one we've been playing with the whole time. And is it reasonable that perhaps that point is actually on that circle? It looks like it. Okay, so I buy that part. But saying walk 1 away from the origin is not enough information. What else do I have to give you? A direction, an angle. And that angle is pi over 3. Pi over 3 is one of our special ones. Is it the first special one, the middle special one, or the big special one? It's the big one. And so small, medium, big. Does it look like perhaps this angle in here is pi over 3? Seems reasonable. I just ballparked it, but they're saying the same thing, okay? So I could either tell you the x and the y, like regular x, y stuff, or I could tell you the r and the theta. We land on the same point. Okay, so let's take a look at number 2. Number 2 says we have these complex numbers. Single 1 by itself, single 4 by itself, and then the crazy one, root 13 e to the 0.8 I. So first thing you want to do is write each number in Cartesian form. That's what Cartesian form means. It's x plus I times y. 1 plus I times 0. That's the only way to make a 1. Fair enough. I can do the same thing with the 4. 4 plus I times 0. But how do you find it for the crazy one? So square root of 13 times what? Oh, root 13 plus I times that angle? Yeah, unfortunately, it's not as clean as that. I wish it were as clean as that. Yeah, that's what we're looking at. You are looking at an r e to the I theta. How do you handle it? Just like we did up above in red. So can you guys do that same thing we did in red, but using root 13 and 0.8? Make sure you're in radians when you use the calculator. Todd, can you say that louder? 2.51 plus I times 2.59. Anybody agree or disagree? Two 2.50. 2.50. 2.598. So should we round that to 2.60? Okay, are we okay with those numbers? 2.5 plus 2.6 I. Any questions on how to get them? Okay, And then it says plot those three numbers. So go ahead and plot each of those numbers on the complex plane pictured. Okay, so did I do that wrong? 2. Oh, I did. Thank you. Okay, something around there. So we get this nice little triangle, 3 points plotted, either thinking of them as x's and y's or thinking of them as r's and thetas. We land on those 3 points. Question so far. Okay, next thing to do is down here in part C. It says find the product of each of those 3 numbers in blue with z. Z was the first number we were talking about all the way up above. C is forever this number right here in this worksheet, e to the I times pi over 3. That's z, okay? All right, so first thing to do is, and we're trying to get these guys to be in Cartesian form. So would you prefer to use this version of those 3 numbers or this version? Remember, Cartesian form is the x plus iy. It seems like the bottom one because it's already in Cartesian form, okay? So we're going to multiply these guys right here by our z from all the way up above. We could also multiply them first and turn them into Cartesian at the end. We'll get the same thing either way. Okay, so let's start multiplying. We have, let's just do the hard one, the complicated one. I'm going to multiply this guy in purple by this guy in red. Multiplying those 2 things together. What silly acronym is going to help us multiply those 2 things? We're going to FOIL. So we've got 2.5 plus I times 2.6 multiplied by, I'm just going to convert everybody to decimals because we're rounding anyway, 0.5 plus I times 0.866. Can somebody verify that for the root 3 over 2? Okay. One and 2. What are 1 and 2? Oh, yes, yes. It's the same z from number 1. Yes. Okay, so we're foiling. What do we get for the first? 1.25. And we have some outers. Which ones are you doing? Okay, so that's the last ones. So what did you say it was? 2.2516, you had said? Okay, we'll just call it 2.25. Anybody have the outers for me? And can you say that first thing but without the root 3 over 2? Just give me a decimal. 2.17, we'll say. Okay, so this is just FOIL. Everybody foiled together. Only thing you have to do is keep careful track of the i's. That's really the only new piece for here. The rest of it is just multiplying two numbers together. What can we do with these middle terms? 2.17i plus 1.3i. Just add them, combine those like terms. So 1.25 plus, what do we have there? 3.47. And then the last piece is that I squared. And forever from this point forward, you replace that I squared with something, -1. So it really becomes minus 2.25. Squaring brings it back to the real numbers, yeah. And then the first and the last things now combine. So what do we get here is -1 plus 3.47i. Is that okay? No. We had bad numbers to start with. We're going to end up with bad numbers. Oh, was it exact? I don't know. Let's see. The 2.5 was a rounded thing. And what else was? Okay, so it was a, yeah, but it's not exactly -1. Topher. Yeah, and so the other ones are actually quite a bit easier because multiplying a number by 4 is just distribute the 4. So that's a lot easier. But I just want to leave it right here and plot this new number. So can you guys plot -1 plus 3.47i? Well, you used to plot 4, but it's been so long that you've kind of forgotten, I think, that like you used to plot points on the real number line, right? Well, even before there was a comma 0, and I don't know when we do this, like back in yeah, elementary school somewhere. But I mean, like like it'll say like plot 1.7, and on which side of that number is 3.2? Which one is bigger? Which is smaller? So we used to plot, and we only needed the one number line for real numbers. But now we need an additional number line to allow us to plot the complex numbers. Yes, the real number line, yeah. Okay, we had said because we were going to Cartesian, let's just look at the Cartesians and multiply them together. That's what we chose to do. Let's make a different choice. Suppose that instead of multiplying them in Cartesian form, we're going to multiply them in this form. So one of them is e to the I times pi over 3. And what was the other one? Right, those are the same two numbers, just written in polar form with r's and thetas. Do we still FOIL? What do we do? Multiply. Okay, I'll put a 1 in there. What numbers get multiplied and pulled in the front? Square root of 13 technically gets multiplied by what number? 1, right? We're just grouping them, and you can rearrange multiplication in any order you want. And then I'll just write the other guys here, 0.8046i, and then e to the, I'll just call it 0.866i. Just root 3 over 2 as a decimal. And then, yeah, what do we do with powers when we see them like this? It's our familiar adding them up rule. So we just get root 13 e to the, and then we're going to add those two. 0.1. Just add them, right? So we're adding those powers, and the i's come, they're just like terms. Okay, that's our answer. Root 13 e to the 1.67 I. Now it's not in Cartesian form, so we would still have to do work. How do you go from this thing to x plus I times y? We do the cosine and the sine, all that stuff. And I guarantee you that you're going to get -1 plus 3.47 I when you do the sines and cosines on this guy in purple. Same number. If we don't care the form of the final answer, which way was easier? The foiling form or this form? This felt a lot easier, didn't it? All we had to do was add the powers and multiply two numbers in the front. A whole lot easier than FOIL. Chris? For, oh, I'm sorry. I was doing the sign and I did root 3 over 2 up there. So let's take back that guarantee because it wouldn't have been the right answer. Pi over 3 is 1 point. Thank you. So let's add that as the correct number. Okay. Thank you, Chris. Okay, with greater confidence, I guarantee if you do the sine and cosine on that guy, you'll get the stuff that we got below when we FOILed. And I sure feel like this is easier. It's easier to do this stuff in polar version than in Cartesian. Somebody wagging their finger. Okay, and the last thing I want to say about this guy is that, okay, so it's a root 13 and it's a 1.85. All right, so root 13, what does that represent in this picture? Remember that, that I'll put a red dot up there because that's where this red dot is plotted on the graph below. So what does that root 13 mean in the picture? It is the real number, but how do you see root 13 in this picture for that? It's the radius, it's the distance here. That's a root 13. Then I've got this 1.85 in front of an I. What is that? That's the angle. It's 1.85 radians. And remember we had said that pi over 2 is the straight up angle, and that's about 1.57. So 1.85, a little bit bigger than this 1.57. So I'll go ahead and put it in there. That's a 1.85. That is your angle. And so the final conclusion here, here's the big question. We started off with this point, this root 13 e to the 0.8. We multiplied it by e to the I times pi over 3, and that gave us a new point. And so the question is, what do those 2 points have to do with each other, if anything? Is there any geometrical thing, like we could have been able to predict, oh, it's going to go roughly over here when you multiply? You're going to do a little bit more of this, hopefully, for practice. Like, we're not going to fill in the rest of this thing right now. But I will say that what's happened is that if you were to actually connect the original point to the origin, that it turns out, maybe I'll undo instead of erasing. Undo. If I connect this original point to the origin, and I look at how did we go from that top blue point to the red point, it turns out it is simply a rotation. And that actually makes sense. What was the radius for the top blue point? It was root 13. What was the new radius? No, root 13. It hasn't gone any further. It's just rotated around. It's on the same circle. And how far did it go? Well, what was this original angle in here? That was originally this 0.8 business. Yes? What's the new total angle? It's 0.8 plus the pi over 3. Oh, of course, you're adding pi over 3 to an angle. You're just swinging around, rotating by pi over 3. And And so it turns out when you multiply complex numbers, it's really just rotating. You are rotating around. And this turns out to be quite useful to people that do computer programming and graphics stuff, because you imagine all the kinds of like every video game involves like points moving around on the screen, right? And how do you make points move around on the screen? Well, maybe it's natural to just do X's and Y's and just say, okay, here's a point, and then move it to this other point. If you wanted to rotate a point, and imagine all the video games where things rotate on the screen, like how do you get a point to just rotate, to like swing around? Well, it's really easy. You multiply it by this complex number, and that's where it lands. And so it's not natural, I don't think, to rotate points in XY land, but I think it's really natural to rotate points in this R and theta land. And so this, I think, is how people do graphics programming, is just multiplying by the right complex number. One little thing, I don't want to imply that whenever you multiply, it just stays on the same circle. Why did it stay root 13 for this particular z? Because of that 1. Right, that root 13 did get multiplied by something. It happened to be a 1. Okay, so normally it's not just a rotate, but it's also a rotate and like stretch, like double or triple or something like that. Okay. All right, can we just try number 14 here at the top? And we'll go to Kyle. Okay, so let's give this a shot. I know you've been dying to know what the 8th root of that number is. You'll sleep better tonight, I'm telling you. This is worth your $110, this moment right here. Good. Okay, so the 8th root of that number, what does it even mean? All right, suppose that I just give a name to the 8th root of that number. I don't know what it is, but I'm just going to call it z. By the way, z is the standard name for complex numbers, like x is the standard name for real numbers. Okay, so I'm just giving a name to that. What does it mean? Well, I suppose it means that if I take z and raise it to the 8th power, I should get something. Does that seem reasonable? Isn't that kind of what the 8th root means? It's find a number that when you raise it to the 8th power, you get the thing inside the radical. Another way to see it is just take the 8th power of both sides of that first equation. All right, so do we buy that? These are one and the same. Okay, so how do we find the 8th root of a number? How do we solve this equation? First, how many solutions are we expecting to this equation? 8. 8. 2. You guys remember something called the fundamental theorem of algebra, which says whatever the degree is, whatever that highest power is, that's how many solutions you're going to get. When you're solving a polynomial equation, whatever the highest power is, like if you solve x squared minus x minus 12 equals 0, how many solutions will you get? You're going to get 2. You've solved that equation a million times. If I make this a x cubed minus x minus 12, how many solutions? That has 3 solutions. Okay, so how many solutions does our equation have? It's got 8. Now this is already kind of strange because, for example, if I asked you for the solution to this equation, you guys know what number to the 5th power is 32? Okay, it's 2. But how many solutions are there to that equation? There are 5. You guys gave me 1. You are missing 4 of them. That is a failing grade. It feels like 2 5 times. There are 4 different numbers that are 5th roots of 32. They are complex numbers. So we're not going to solve that, but you'll be able to after this. It's one of the group activity things down below. But we're going to solve this guy. We're going to find 8 answers, although we'll probably bail out after a couple. All right, so here's what we're going to do. No idea how to solve this thing in this version, but what I'm going to do is change things to polar. And you guys actually already yesterday gave me the -5 minus 3i in polar. Can you look it up? I think we found it during class last time. E to the 211i. Okay, so this is what we did. We were in degrees last time. This was doing the r squared equals x squared plus y squared, and tangent of theta is y over x. We did it. Okay. We did that particular number last class. Yeah. Okay, so just writing that guy in r e to the I theta. I'll put the degree symbol once, but I'm not going to write it every time. And you know what? Then it feels like this z over here should also be in r's and thetas. Now I don't know what it is. I don't know the answer. The answer is whatever z is, but I'm just going to put like a generic re to the I theta for r to be determined and for theta to be determined. And then on the left-hand side, we have familiar powers of exponents. What can we do with that 8? We're going to bring it in. We're going to multiply. So what happens with this r? It becomes r to the 8th, e to the, and then what do you do with powers like I, theta, and multiply them? So do you guys buy, I don't know what order I should write this in. I'll do it that order. You multiply the 8 times the I theta. Any questions so far? Okay. And now I feel like I'm really in trouble because I have 2 unknowns. What are they? R and theta. But I have how many equations I'm working with? I have 1 equation here at the bottom. 1 equation with 2 unknowns? I don't know. But I do know, I feel like I should be setting little pieces of these things equal to each other. What do you think r to the 8 might equal? It feels like it might equal 5.8. And then on the other side, 8 theta equals 211. Aha. Equations that I can solve. So we're just making the pieces equal to each other, the ones that look like they should equal each other. R to the 8th is 5.8. And 8 theta is 211. How do we solve the first equation? A through to both sides. Or if you don't know how to type that on the calculator, you could do to the 1/8 power. What do we get there? 1 point. All right, so we'll say 1.25 roughly. Yeah, so then we get into the, well, you know, actually how many solutions does that equation have? That equation has 8. Okay, but that r was defined to be a real number. That equation does not have 8 solutions. If r was a complex number, it would have 8 solutions. But if it's a real number, it actually only has 2. Hassiday points out correctly that there's a plus or minus you should pick. Well, we have a choice. You can pick whatever you want. I'm going to pick the plus. Pick the minus if it suits your fancy. I like walking in the forwards direction. It's easier for my brain to handle. So I'm going to choose that r. And then we're going to solve for the theta. How do we solve for theta? Divide by 8. So send this guy over here. Theta equals 211 over 8. So theta is 6.4. Fair enough. Okay, and putting all that stuff together, I think we just found one answer anyway. Started off by letting z equal this generic re to the I theta. What did we find for r? It was 1.25. E to the I times, what did we find for theta? 26.4. Okay, that number right there is an 8th root of negative 5 minus 3i. Meaning, if you take it and raise it to the 8th power, if you take that red number and raise it to the 8th power, what should we get? You should get negative 5 minus 3i, or 5.8 e to the 211i, either way. If you take that thing and raise it to the 8th power, you get what you wanted. You get what you started with. So let's let the calculator help us just a little bit here. And we'll try to confirm this thing. Okay, so what did we say it was? 1.25. 1.25 second e to the I times 26.4. Now we need degrees, so let's make sure we're in degrees. You don't need to type it, but so I've got my number right here. Let's see what it does if I hit enter. It says that. Okay, so that's the X and Y version of the answer. And if I take it and raise it to the 8th power, what should I get? Take the answer and raise it to the 8th power. I should get that negative 5 minus 3i. Okay, we have significant rounding issues, but that's not what I'm after here. What did we say we were going to get? Negative 5 minus 3i. That seems quite significant. Yeah. Yeah, maybe that's it. It could just be that's it. If I raise it to the 8th power. 5.9. I see my 5.9 is like 5.8. It's significant rounding, but we could do better if we stored numbers in the calculator. I'm just sort of after this general process here. But I promised you how many solutions? 8. How many did we find? 1. How do we find the other ones? Well, this 211 degrees, is that the only way to think about the original point? No. What could we add to 211 and land on the same angle? 360. Now, if you added 360, I will put it here in green. If you added a 360, you would now have, what, 571. What would you do to find theta? You divide it by 8. Super, 571 divided by 8. I'll say about 71.4. That's a different angle. It's different than the 26.4. Stick that guy up there in the red, and you'll have another answer. Instead of adding 360, what could we have added? 180? No, I'm just looking for different angles that land exactly on 211. Couldn't I have added a 720 instead of a 360? And in fact, I'm already bored with this game. What did we put on before? Didn't we add like a 360K? You can add any 360s you want. And so then if we bring this over here, it's really 360K divided by what? 8. And how much is 360 divided by 8? What is it? 45. So really, the solutions look like 26.4 degrees plus as many 45s as you feel like writing.
And once you get back around to equivalent angle,
then we're done. Yeah, so you're going to do 8 of these. There will be 8 different numbers. Then eventually you'll come around to 26.4 plus 360. And that will be the 9th one, which is equivalent to the first one. Did these two numbers, the 26 and the 71, do they differ by the 45? Yeah. Okay, so this is how we solve for 8th roots. And in fact, if you wanted to know what the other 5th roots of 32 are, you follow this exact process. Any questions on that? It becomes easy with practice, but the first time I tried it, I was like, wait, what do I do? Well, I guess the second time I tried it, wait, what do I do next? Like every step seems reasonable when somebody's walking through it, but yeah. Yes. So yeah, every one of these is going to have a 1.25. You're going to have 8 different thetas to give you your 8 different answers. R to the 8th does have 2 answers. It's a plus or minus 1.25. You could, instead of walking 1.25 at an angle of 26, we could send it to the third quadrant backwards. There's only 8. Yeah.
I don't get how 32 has 8 answers.
No, this guy has 5 answers.
Oh, how do you got 5 answers if you're not talking about?
Yeah, so what you could do for 32 is you could write this guy. So the same idea as before. We'll make it some general r e to the I theta. That's my x getting replaced by some generic polar complex number equals. Now you got to write 32 as a r e to the I theta. So think about where the number 32 is when you plot it. There's the number 32, right? What's the r? How far from the origin is 32? E to the I, what's the theta? 0. It's a 0 angle. There you go. Now you follow the process just like you did before. And you will find the number plain old 2. That's going to be one of your answers. But then you're going to find 4 others that have I's in them. Topher. Yes. So Topher is just giving us the cis theta version instead of the e to the I theta version, and they're the same. So absolutely. I would say give me answers in polar form or give me answers in Cartesian form. I would be clear if I wanted all the answers. Okay. All right. So okay. So we're going to end our complex number stuff there. I know it's not super exciting, but it is what it is. I want to show you something just as like a quick thing before we jump to the next section, which is about vectors. So I typed in a crazy equation. This is recording. Y equals. So I typed this equation into my calculator. So so this is in polar form, right? R equals. So we did a little bit of polar graphing last class. You guys ended up drawing like these circular things and these spirally things and like flowers with petals. And so, so I found this equation in a book. In fact, it was the book that Tassiday brought in that we projected way back when, where we looked at slide rules and the first scientific calculator. So later on in that book is this equation. E to the cosine theta minus 2 cosine 4 theta plus sine of theta over 12, that last term to the 5th. And so, so I'm recording this, and if you feel like checking it out later on, you can type that guy in. And you can also type in this window. I'll just project it here for a moment in case you watch the video and you feel like typing it in, and then we're going to graph it. And then we're going to change to radian mode so it actually does something. Mode, radian mode. Then we're going to graph it. What does it look like? Butterfly. So that equation, that single equation, traces out something that looks an awful lot like a butterfly. And so, so I did that on the calculator, but then I wanted to get some color. And so I did something on Sketchpad. It's the same equation up here, just with a few extra letters, but it's that equation. And so, so if you actually have hidden it, but anyway, there's the graph, and it's the same graph as before. But what I wanted to do was actually get this thing to sort of draw it for me. And so I've got all these points that kind of fly around, and they're little painters, and they're cheap, so we can let them run all day. And then what we do is we make the A a little smaller. We're just going to make the butterfly a tiny bit smaller. And then we're going to run them around again. But I made it so that the painters change color when they move. So now they're all kind of yellow orangish, and then we can make it smaller still, and then we'll get some greens. And it is pretty, isn't it? Is this worth 110? Hillary got a Hillary got a Hillary got a speeding ticket this morning, and so she said she needed, yeah, so we needed to give her something real nice to feel like it was worth coming in. So anyway, so a bunch of nested butterflies, and they all come from a polar graph equation, and I cannot imagine some y equals f of x equation that would give us anything like that. Can't imagine. All right. Thorns on the stem. You guys just want it all. All right, can we jump to the bottom of page 29? 29. Okay, so I have updated the calendar. I can reprint it if people want it reprinted, and it's totally fine if you want it reprinted. I just moved stuff down a day because we decided we were going to take a little more time to do complex numbers. So, so we're going to start vectors. We're not going to finish them today. The homework for tonight is the complex numbers homework. Nothing is due now, but the complex numbers homework is due Monday. And then the next class, I'll give you the vectors homework, and we'll be, a little bit in between for a few days. So I guess the only things I want to point out to you from this new calendar is that the test has now moved from the day that I had said on the first day of class, okay? So our test is now May the 2nd. That's probably the only significant change, I mean, like the quizzes have gotten pushed back a little bit. I'll just reprint it. You don't need to grab everything. I'll print it and bring it Monday. Yeah, I guess technically the project has pushed back. I'd encourage you to not just let that project linger. I mean, you've had the tools to answer this project for like a week now. So sure, if you want to turn it in on the 25th instead of the 23rd, that's fine. But maybe get it out of the way. I mean, you have all the stuff you need to do to answer it. Okay, any questions on the schedule? Yeah, you could turn it in earlier if you want to. It's not a math project, it's a reflection on the semester project. So you could do it week, 2 weeks ahead of time if you wanted. All right, so we are back here on page 29, and we'll start here at the bottom with vectors. Can we go to Vance? Okay, Garrett?
These quantities often represented by an arrow incorporating both magnitude and the arrow direction.
Okay, and so we'll just pause for 1 second. Magnitude and direction I guess we haven't been talking about magnitude, but haven't we been doing an r and a theta, which has represented how far you are from the origin and the direction that you're supposed to go? It's going to be exactly the same thing. In fact, there's really not a whole heck of a lot that's new in this section, as long as you can grab on to this r and theta stuff that we've been playing around with. Okay, so we'll go to Chris for 2. Okay, so if I just write down x, then in your mind you are thinking x is just some real number. But if I write x with a little arrow on top of it, now you are thinking that x represents a new kind of thing, something called a vector. And so we're going to talk about these, but just so that you see the notation that you're going to see in the book, those things don't mean the same thing. X is a real number. X with an arrow over it is going to mean one of these quantities that we're going to describe here. Richard, number 3. Okay, so we've got this chair right here. We'll go to Kate. Okay, so 2 feet east, let's assume east is to the right. So 2 east and 4 south, can you figure out where the chair is now? So it's at the point 2, -4, right? And the way to kind of graphically represent the motion that's happened is just a little arrow. And you put the beginning of the arrow at the starting position, and then you put the other part of the arrow at the final position, and then you put that arrowhead just so we know which way it headed. because she could have decided to move it back and then it would be the same arrow but pointing the other direction, okay? And so that arrow right there has two components. It has a length and it has a direction. Is the length 2? Is it 4? How would you find the length? Right. Square root of 2 squared plus 4 squared. It's Pythagorean theorem, or it's the formula we've seen for r. It's the same kind of idea as a velocity, and we'll see some of that too. So it's got a length and it has a direction. And if I really wanted to think about a direction, I might be able to find that angle right there. Right? So Sandy, okay, you're supposed to move it, I don't know, 5.8 feet and go negative 60 degrees. A length and a direction. That's what a vector is. Tacite for B. Okay, starting from the previous position, don't go back to the origin, but draw a new vector representing the second push. Okay, so we said 6 west and 4 north. Does that land me here? And then an arrow again in the direction of travel. And I'll say something about these arrows here. Their lengths represent something. For which of those pushes did Sandy do more work? Second one. You can just look at it and see that it is longer, right? So longer means more work. Or if these things were velocities, maybe you say your original velocity is 5.8 meters per second, and then your next velocity is however long this one is, 7 meters per second. You're going faster the second time, okay? So the bigger the thing, the more oomph it has, whatever that oomph represents. And then, you know, being good mathematicians, we could say, well, Sandy, that was not a very efficient thing. Maybe you took this little detour because you thought it would be better in the first spot, but really, what should Sandy have done? Probably should have done this. And so we could say, all right, next time, Sandy, if you're going to do that, save yourself some work and just go 4 west and 0 north or 0 south, something like that. Okay, so just for the notation business, you see this V with a little arrow over it. It represents a vector. And W with an arrow over it is the other vector. Yeah, V and W are pretty common. U is also pretty common. Generally, we avoid the X and the Y because we've got such associations with X's and Y's already. Okay, we'll go to 4 for Sam. Okay, so we found the sum of two vectors. We didn't think about adding anything, we just drew a picture, but we drew it in such a way that we really did add, because we looked at what you did in terms of the purple, and then from the purple we added this red vector. And the final result, the sum, the resultant, was this green vector, okay? So it's perfectly good to say that V plus W equals that green vector. So this tail to head business, the tail is the starting point and the head is the ending point. I can never remember which word represents which. I'm not going to ask you to either. But anyway, tail to head, what that means is that for the red vector, what did we start with? Yeah, so the red vector, we started with the tail, of course, but where did we put that tail? At the head of the other vector. So that's why we call it the tail to head method. But just draw them in the natural way and don't worry about the names. Okay, let's try 5. We're over to Todd. Okay, so let's take a look at this picture right here. So we've got this car and it's being towed, and maybe you have two people pulling it, or maybe you have two machines pulling it. And those machines are pulling this car at a certain force, the magnitude, 4 kilonewtons, that's like a pull, and at an angle. So that first machine up there is pulling at a 30-degree angle with a strength of 4 kilonewtons. And then the bottom machine is pulling 25 degrees with a strength of 2 kilonewtons. And ultimately, I want to know where the car is going to go. So do you think that the car is going to go, okay, first, one thing I don't like about this diagram, and I'm going to change it next time I teach the class, but I don't like that what does it look like is true about those two vectors? They look like they're the same length, and they're not. So let's actually draw it maybe a little bit better. So how about we say that this is our 2 kilonewton one to kind of show that it's half the length of the 4. There's information that you're supposed to get from the picture, and this picture is deceiving. So I suppose it's reasonable to say that the car is going to move in a direction that is somewhere between where these two machines are, right? Someplace in this space is where the car is going to head, right? I mean, it's not going to go backwards. It's not going to go straight up. It's going to go somewhere between them. So do you feel it's going to go straight to the right? Or do you feel like it's going to go more down? Or do you feel like it's going to go more up? 2 votes for up. Other votes? Yeah? Up, up. Lots of votes for up. Why is it going to go up? Yeah, actually, both of those things, it's a really nice observation. Both of those things are giving the top thing the advantage. The top machine is pulling stronger, so it's already got an advantage, but it's also pulling at a steeper angle. So it's really, really trying to pull up, whereas the bottom machine, okay, it's pulling down, but it's also kind of pulling to the right, maybe more than the top one is. So yeah, I think this guy is going to go someplace, like I'm not going to say so extreme as that, but maybe something like that. Where will it get? Is it treated like an asymptote? It's a good question. What do we think? Wobble? Okay, so there's some complicated motion that could happen if these machines just kind of stayed there and kept pulling at these angles. Let's assume that this whole picture just gradually shifts to the right. Like these machines are just going to go, they're just going to walk to the right, at just the right speed so that the picture kind of always looks like that. So the angles don't change and the forces don't change. Do we feel like it's eventually going to make its way up to there? Yeah, given this new condition, I kind of feel like it's just going to go at some straight line.
I feel like if that was what was happening in real world conditions, because it's 22 code.
Mhm. Right. Yeah, and I think that's kind of what Kyle was talking about, where the angles might change and things might not be the same. I want that to be my picture. I want to analyze that picture as it is. And if I can just analyze that picture.
Do ivory tower, folks.
Yeah, yeah. Okay, so let's see if we can analyze this picture. I was going to do this in a certain way, but we're going to skip to the more important way. Here's the more important way. We're going to take that 4 kilonewton force at 30 degrees and just analyze it. I want to know how much of that 4 kilonewton force is pulling straight to the right and how much is pulling straight up. That's really what's happening here. That machine right there has a horizontal component and a vertical component. And the net result is this 4 at an angle of 30 degrees, but we're going to split it up. So let's see if we can't split it up. I'm going to drop this thing straight down here. and then straight to the right. I'm ignoring the 25 part for right now. And I've got a very, very familiar looking picture. If that's a 4 and that's a 30 degrees, can you find the lengths of the two green line segments? Feel free to use the calculator here. Even though 30 is nice, 25 isn't, so don't worry about unit circle. All right, so we use these formulas, which we all know so well. And so this is just not using SOHCAHTOA. This is using the same, it's equivalent. So, but this is how physicists write it. So let's write it this way. So we go 4 cosine of the 30 degrees, and then down below it's 4 sine of 30 degrees. And in fact, it's always those two formulas because the x is always the r times the cosine of theta. So even though, yeah, absolutely, you can use SOHCAHTOA, I just don't even think about it. I just use these. It's like automatic. It is SOHCAHTOA, but it's one step less, I guess. SOHCAHTOA, you have to solve for, you'd have to do work to solve for the opposite or to solve for the adjacent. Yes. Yes, yes, it looks like this. Absolutely. So what did we say here? 3.46? Okay, and then the bottom one was exactly 2. And so what that means is that top machine is pulling to the right with 3.46 kilonewtons of force, and separately it is pulling up with 2 newtons of force. Does it make sense that more of the pull is to the right than up? Yes, because that angle is pretty small. But if I were to make it like a 50-degree angle, now all of a sudden it's more up because 50 degrees is more up than to the right. Okay, so those numbers seem reasonable. Does it also seem reasonable that neither of them is bigger than 4? Yeah, 4 is the total thing, and it's got 2 different pieces that somehow combine to a result of 4, but neither of them is 4. Let's do the same thing with the piece down below. So again, I'll mark in green as the horizontal. In fact, we'll do that in blue. So blue is going to be that horizontal, and then black is going to be the vertical. And I will encourage you to use these two formulas right here, which we get right every time, or cosine theta. But one little detail, how much is theta? Theta is not 25. How much is theta? Theta is negative 25. There's no axes there, but there are, right? If you're going to put axes somewhere, that seems like the place to put them. And if you go 25 degrees clockwise, that's really a negative 25-degree angle. So how much is r for this one? 2. So we go 2 cosine negative 25. How much? 1.8? 1.81, thank you. And then 2 sine negative 25. Negative 0.85. Super. How much is that bottom machine pulling straight to the right? 1.8. How much is it pulling up? Negative 0.85, or down 0.85. And here's the really nice part, is that when you break the vector up into its components, that's what the x and y pieces are called, then you can mush them together in a natural way. It wasn't clear to me how these two vectors were going to interact because I can't handle the 30-degree angle and the 25-degree angle, and one of them is pulling with a 4 and the other one is only 2. But x's go with x's and y's go with y's. So to find out what the net result is, the sum is, we get to just add these guys up. So we're going to do that over here. And we'll say the sum of the two vectors is to add these guys up. So what were the x's? 3.46 plus 1.81. The fact that they're both plus means these guys are working together in which direction? To the right. They're both pulling this thing to the right. They agree that this car should be moving to the right. So 7 to 5.27. And how about the vertical? What was the top part? 2. And the bottom one? Negative 0.85. And this says, what are they doing in terms of the vertical? Are they working together or not? One of them is trying to pull up, the other one is trying to pull down. The signs take care of it, but only if you included a negative for that 25 degrees. Make sure you put negatives if this thing is clockwise. Okay, so what is the car really going to do? It's going to move 5.27 to the right for every 1.15 up. That is what the car is going to do. Like a function? What do you mean? Yes, it is a linear thing. Yeah. Okay, and then how about the last piece of this puzzle? If I were to draw that thing, we said 5.27 and 1.15. I'm just going to plot it here like as an ordered pair. It's natural. It says go to the right. It says go up. But really, that wasn't how the picture started, right? The picture started with 4 kilonewtons at an angle of 30 degrees. So what do you think you could find given these two numbers here? You could find the R by doing Pythagorean theorem, a squared plus b squared. What else could we find? You could find the theta by doing, remember which trig function gives you the theta? It was the tangent, right? It was the tangent, inverse tan of y over x. So it's real easy to go backwards once you have these components. Okay, we'll do plenty of this. None of the homework for tonight is on this. Just do the complex number stuff and have a wonderful weekend.